Let's move on to our third speaker. Great. So our third speaker today is Marius Oetting. Marius is a postdoc at Bielefeld University in Germany. His research focuses on the development and application of statistical tools tailored to specific sports-related research questions. His current topics include betting markets, with a focus on fraud detection, interesting, and the analysis of soccer tactics using tracking data. Today, he'll be talking about a Copula-based hidden Markov model for classification of tactics in football, presumably soccer. So welcome, Marius, and please take it away.
Hey, yeah, hi, thanks for the introduction, and yeah, thanks for having me here today and for the opportunity to present my work here at the NESSIS conference. Yeah, so my talk is about a Copula-based hidden Markov model for classification of tactics in football, and this is joint work with Dimitris Kalis from Athens University. And yeah, Kevin, as you just mentioned, so my title includes the word football. What I actually mean by that is soccer, so sorry for the potential confusion. From now on, I will simply use the word soccer. Yeah, so let's start with a motivating example here. So one of the major soccer tournaments in Europe is the UEFA Champions League. And next week, there will be the next round of matches. And on Tuesday, there will be the match Atletico Madrid against FC Liverpool. And imagine that you're an analyst and that you're working together with the coaching staff of Atletico Madrid, and you're asked to provide some kind of analysis about your next opponent, so about Liverpool. So what you could do as a first step is to simply have a look at their previous results. So here we see the previous 5 matches from Liverpool, and we see, okay, they were quite successful and they scored quite a few goals. And in their last match in the Champions League against Porto, they even scored 5 goals. But yeah, simply by looking at these numbers, it's a bit hard to gain some further insights because, I mean, but just by looking at the numbers, we don't know how these goals were actually scored, or so were these goals scored based on build-up play, or were these goals scored based on counter-attacks. So we simply don't know. And in soccer, of course, there's a bit more than scoring goals. So if we then go one step further, I mean, what's also interesting is how goal scoring chances are created. So how does your opponent, how does he do that? Do they play counterattacks, or do they create goal-scoring chances based on build-up play? And what's their general style of play? So are they playing more offensive or more defensive? And say if they are playing defensive, what style of defending do they play? So do they play pressing, or do they park the bus, or what do they do? And all these questions are rather important when you analyze future opponents in soccer. But these questions are usually investigated by rather time-consuming video analysis. So usually for these questions, hours and hours of video analysis has to be undertaken in order to get an idea of the playing style of future opponents. So here in our project, we used tracking data, and we used this tracking data to automatically detect a team's playing style. So here we aim at a data-driven approach to use statistical modeling to help the video analyst to automatically detect the playing style of a team. So, for example, of a future opponent by analyzing tracking data. And for that, let's have a brief look at what tracking data in soccer looks like. So I guess you're all familiar with tracking data. So our data set here contains the X and Y coordinates of all players sampled 25 times a second. So in this snapshot here of our data refers to the kickoff. So here we see all players and the ball in the middle. And then we can, of course, also have a look at another snapshot here of our data. So this is like the first second of the match where the first pass is played and all players moved a bit. And we can also like glue these individual snapshots together, such that we have an animated graphic here where we can follow the match. And we see here now that the blue team, they're having the ball and they're making a shot on the goal and manage to keep possession of the ball, pass the ball into the box, and then they will score their first goal. So these figure here, this graphic was also created based on our tracking data, but we do not want to watch the entire match based on that. we instead want to investigate tracking data to make some inference about the underlying tactics of a team. Of course, we're not the first to investigate tracking data in soccer, so there's been lots of work done, as we've also seen in the previous talk here. So lots of studies focus on passing or shooting performance or on team formation. Space creation is also considered as one of the major skills of a soccer player. And there's a very nice review paper on analyses which have been carried out using soccer tracking data. And this was published last year by Gose et al. Okay, so what kind of data do we use here? So we use data from one match, so tracking data from one match, which is freely available online. This data set has been provided by the company Metrica Sports, and they uploaded this data set to their GitHub repository. And yeah, this tracking data set includes the X and Y coordinates of all players and of the ball. And yeah, we have a sampling frequency here of 25 Hertz, or 25 observations per second. So overall, we have data on all 22 players and of the ball. We have 90 minutes plus some stoppage time of play. We have 25 observations per second. So all in all, we have about 3 million individual data points here for one match. But yeah, how do we use this data in order to make some inference about the underlying tactics of a team? So the first step is that we consider the so-called effective playing space. And this is simply the convex hull, which is spanned by all players, excluding the goalkeepers of one team. And we see here in this example figure that we have the convex hull here of the black team, which has also the ball, and this convex hull, so this EPS, this effective playing space, is much larger than for the blue team. So the blue team, they are defending here and they are convex hull, so their EPS is much smaller. So to get an idea how different tactics in soccer refer to the EPS, we can simply have a look at some example situations here. So here we see 4 situations. The one on the top left is the one we have just seen on the previous slide. The one on the top right here in panel B, this situation we have actually already also seen because this was included in the animated graphic. So here in the next second, the player here scores a goal. And what we see here is that the blue team, they are the attacking team, and their EPS value is larger than of the opposing team, than of the black team, which are defending here. For panel C, we see that the black team, they are having the ball. And what's now a bit different compared to panel A is that the defending team, so the blue team here, they are now not standing closely to their own goal, but they are attacking the ball carrying player, and they also mark to some extent the other players. So they're playing in defense here, but what they do is they attack the ball carrying player, they mark the other players, and by that they increase their EPS. So if we compare panel A and panel C, then we see that by increasing or by marking the other players and by attacking the ball carrying player, the EPS is increased compared to panel A. And panel D refers to a standard corner kick. So basically two things we have to keep in mind when investigating these data or these EPS. So the first one is that if a team is attacking, then this team has usually a larger EPS value than the team which is defending. But if a team is defending and standing closely to their own goal, then the EPS value is rather small. But if the defending team is attacking the ball carrying player and marking the other players, then the EPS is a bit increased. So this will be also important later on. Again, so of course for the EPS, we also measure the EPS with a sampling frequency of 25 Hertz here. We have 90 minutes of play plus some injury time, so 97 minutes here in this example match in total, which gives us 145,000 observations. But I mean, as we all know, in soccer, we have lots of periods in the match where players are injured or discussing with the referee or preparing for a free kick and so on. So that's why we consider only those observations where the ball was indeed in play. And this then gives us 88,000 observations here in total. And here we can have a look simply at the time series of the data. So in the top panel, this is these are the EPS values for team A, so for the blue team, and on the bottom these are the EPS values for team B, shown in black here. And what we see is that, for example, here for team A, around minute 50 or 53 maybe, there's a period where the EPS values of team A are rather large, but we see that there are also periods here in the time series for team A, so for example around minute 60 or 65, where the EPS values are rather low. So there are periods in the match where we observe larger EPS values, and also periods where we observe lower EPS values. And this holds also for team B. So for team B, there are also periods where they have a rather large value of the EPS, and we observe also periods for team B with lower values of the EPS. And yeah, this is kind of important when we think of our modeling framework here, because of this fact that we observe these periods with different sizes of the EPS. We consider hidden Markov models here because hidden Markov models naturally accommodate the idea that a match progresses through different phases. So we have then two stochastic processes here. So the first one is shown here on top. This is simply, these are the time series of our response variable, so of the EPS, of the effective playing space, denoted by Y. And we assume that the values of the EPS are driven by an underlying latent state. And this underlying latent state here serves for the underlying unobserved playing style. So, I mean, if we would watch the match on TV, we could, of course, have some idea about the playing style, but here we only have the tracking data, so we don't know the underlying playing style. So this is unobserved. So, for example, if you consider that a team is playing in offense, so if the underlying latent state would be an offensive style of play, then we would expect to observe larger values for the EPS. Whereas if a team is playing a more defensive style of play, then we would expect to observe lower values for the EPS. And for this states here, we assume that the state at one time point t depends only on the state at the previous time point, at time point t-1. And for the response variable, so for the y's, we assume a gamma distribution here, simply because we have a continuous valued response variable with values which are larger than 0. So this is like a natural choice here. And we use parameterization of the gamma distribution where we can directly interpret the parameters. So we will have a mean mu and a standard deviation sigma. Okay, so how does that look like then if we fit a very simple model to our data? So here in the first step, we fit a model to the data from team A and to the data from team B, and we select only 2 states. So the number of states is something we have to select beforehand. So here in state 1, then the mean for team A for the first state is 1,250 square meters. So EPS of 1,250. So this is a rather large value, which may correspond to an offensive style of play. Whereas in the second state, the mean is about 700, so way lower compared to the first state. So this could be interpreted simply as a more defensive style of play. And we observe similar values then for team B. So by now, I mean, we have fitted a simple model, but there are 2 major drawbacks here. So the first one is that we do not consider any potential interaction between these 2 teams. So, I mean, if we think of a soccer match, the 2 teams are playing on the soccer pitch, and of course they are interacting with each other. So if one team is playing more offensively, then the other team is playing more defensively, and vice versa. So we have to somehow account for these dependence. And we may also have different tactics. So there might be something in between offensive and defensive. So we may have a third or even a fourth or a fifth state. Okay, but let's first consider the first point with the dependence. So here we use a bivariate model. So now we consider both of the observations together. So we model them jointly here. So we have then a bivariate time series. So at each time point t, we model the EPS of team A and the EPS of team B. We model them jointly. And within our hidden Markov model, we allow then for within state correlation between the 2 teams' EPS by using a copula, which is denoted by C here. And a copula is simply a multivariate distribution function, which has uniform margins. And the Copula allows to build very flexible, or in a very flexible way, multivariate distribution. So in our case here, a flexible bivariate gamma distribution. So for both teams EPS, we still assume a gamma distribution here, again with mean mu and standard deviation sigma. But now we also have the potential dependence, or we explicitly model the dependence between the two teams by incorporating a copula here. And there are lots of different copula forms available in the literature. So we select the Frank copula here just for illustration. And we then end up with one additional parameter theta. And this parameter theta has like a nice and intuitive interpretation. So if theta is almost 0, then this would mean that we have independence. For values of theta smaller than 0, we have a negative dependence. And for values for theta larger than 0, we have a positive dependence. So this theta parameter, which measures the dependence, can be interpreted very, very nicely and very straightforward. Okay, so now the first point is taken. So we now have included interaction between the two teams. The next one is, how many states do we actually need? So the states, they serve for the underlying unobserved tactics of a team. And it's, the question is, how many states do we actually need? So how many tactics are there? And if you're a match analyst, and if you working together with some professional teams, you may have a very good idea of how many playing styles there are. Here, unfortunately, we have no prior information on that. So here we simply consider models with 2 up to 5 states. And the computational cost for fitting a 2-state model is very low. So here it only takes about 7 minutes to fit such a model, but on a standard desktop computer. But if we fit a 5-state model, then this already takes 4 hours. And this is because the number of parameters, they grow exponentially once we add more states. And to choose the number of states, we could consult information criteria like AIC or BIC. And these two, they point to the 5-state model here. And it's like a bit of a well-known problem in hidden Markov models that those information criteria, they often select mostly over-complex models, as shown is also here in this case. So the AIC and BIC, they also point here to the 5-state model. But instead, we simply have a look at the fitted state-dependent distribution. So on the left, we see this the 3-state model. In the middle, we see the 4-state model, and on the right, we see the model with 5 states. And we see that here for the 3-state model, there's almost no overlap. For the 4-state model, we have a moderate amount of overlap between these two distributions. And for the third figure here, so for the 5-state model, we see that there's a substantial overlap between some distributions. So for example, here, the 4th state, there's some overlap between state 4 and state 3, and also between state 5 and state 4. And what does that mean for our football, for our soccer analysis here? So this means that if there's a huge overlap, then this makes the interpretation of the states and hence of the model very, very difficult. And if it's not that easy to interpret the states, then we have a problem here, because then we can't really distinguish maybe between different tactics. So it's very important for us that we have states which can be nicely interpreted. And that's why we've chosen then here the 4-state model, because the amount of overlap is still moderate here. So here we then select 4 states. So let's have a look at how this fitted model then looks like with the 4 states here. And these are the parameter estimates. So let's first start with state 1. So with the first column here, we see here that the mean for team B is fairly large with 1,230 square meters. For team A, the estimated mean is only 650. So here we have, again, like a clear interpretation. This may refer to situations where team B is attacking and team A is defending. And a similar situation we have in state 4, just the other way around. So just flipped. Here, team A has a way larger mean than team B. So here, team A is potentially attacking and team B is defending. For states 2 and 3, the situation is maybe not 100% clear here. Because here, let's start with state 2. Here we see, okay, the mean of team B is larger than of team A. But the difference is not that large here. So this could, again, refer to team B attacking, because their mean here is larger. But this could refer then to situations where team A is pressing, because we've seen in the exploratory analysis, if a team is not if attacking, so if a team is defending, but if their EPS values are somehow comparable or in a comparable range, then this may refer to situations where the opponent is then pressing. So that's why we end up here with the interpretation that team B is attacking in state 2 and team A is pressing. And for state 3, it's just the other way around, where team A is attacking and team B is pressing. And for all states, we observe a positive the positive dependence, or the dependence parameter here is estimated positive in all states. Okay, so let's then like go one step back. So our initial aim was that we wanted to automatically classify a team's underlying playing style or a team's underlying tactics based on this tracking data. And for that, we use the so-called decoded states. So we use an algorithm here which calculates the most likely trajectory of the underlying states. So then we have, for each time point, we then have an estimate on the most likely state, which was most likely active at that given point in time in our match. And we can then simply have a look at some example situations here. So we can have a look, okay, which kind of situations were classified as state 1 from our model. So state 1, we carried out the interpretation there that team B is attacking and team A is in defense. And so team B is the black team, team A is the blue team. And here we see that this fits to our interpretation. In state 2, we see that so the interpretation was that team B is attacking and team A is pressing, and compared to the first row, we see that here in these example situations, the players of team A, so of the blue team, they're standing a bit more close to the players of the other team. And for states 3 and states 4, the interpretation is again the other way around. So in state 3, team A is attacking and team B is pressing. So here we see, okay, team A, they're having the ball, and team B, the team shown in black, they are standing fairly close to their opponents, while in state 4, in these example situations, team A is attacking, they have a large value of the EPS, large convex hull, and the team in defense, so team B, they're not attacking the ball carrier, they are standing very, very compact and close to each other. Okay, but we can, of course, not only have a look at example situations here, but we can also have a look at the sequence here as a whole. So this is, again, the time series for team A and team B, so the EPS values, which I also showed you in the beginning. But now we have color-coded here the underlying decoded states. So here we could simply have a look. For example, here we see lots of orange points here at the beginning at around minute 20. We see some orange lines, and this refers to state 1, where team A is defending and team B is attacking. And based on that, we can simply investigate how goals were scored, for example. So here these blue lines, they refer to goals scored by team A, and the black line, this refers to the goals scored by team B. And for example, here for the second goal scored by team A, so we see lots of yellow lines before that, and yellow means, okay, team A was attacking and team B was defending. So here we can simply pick one specific situation in the match and can then visually inspect what kind of state was active at that time. So what was the playing style of team A and what was the playing style of team B at that time point. We can also count all these decoded states together, so to have an idea how much time is spent in each state. And we see here that most of the time is spent in state 4, where team A is attacking and team B is defending. We've seen on the previous slide that team A, they scored 3 goals, team B scored only 1 goal. So it seems like intuitively plausible that here we observe that most of the time the match was in state 4, where team A was attacking, because they scored 3 goals. This seems plausible. Okay. What we can also do is to have again a look at some kind of animated figure again. So we can again have a look at how goals were scored. So we will have a look at the first goal. So this is the situation I showed you in the beginning. Here on the top left, you see the frame number of the match, and then you see the decoded state. So our model says here all the time for all frames, okay, this is state 4, where team A is attacking. So the blue team is attacking and team B is defending. And this interpretation or this decoded state here does not change here across this sequence, but we see, okay, this fits to what we see on the pitch. So the blue team, team A, they are attacking here, and team B, they are defending. So this is basically the same sequence I showed you in the beginning. But yeah, to show you some other sequence where the decoded state also switches, we have a look here at that. So here we start with state 4, where team A is attacking and team B is defending, and then our model switches back to state 3, where team B is now pressing. What might discuss whether this is indeed pressing what we see here. So here the sequence starts again, and at the beginning of this sequence, our model says this is state 3, team A attacking and team B pressing, and then after a few seconds, it switches to state 4, where team A is attacking and team B defending, which seems to make sense here. But now in a few seconds, the decoded state will switch again to state 3. And whether this is indeed pressing of team B, one could argue about that, whether this is indeed pressing here. But this is some kind of model check here. Also for us, because if our model would say to these situations, or would assign these situations to, for example, state 3 or state 2, where team B is attacking, this would not make any sense if we would say here, okay, we see team A is attacking, but our model says team B is attacking. So this wouldn't make any sense. So having a look at these animated figures together with the decoded states can also can be seen here as some kind of model check to see whether our model is really able to classify such situations correctly. Okay, coming to an end. So in my talk, I showed you a tool to classify tactics in soccer to do that automatically based on tracking data. An important point I want to highlight here is that our attempt was not, so our main aim was not that we wanted to classify all observations correctly. I mean, this would have been nice, of course, but we only have data here from one match. So the main aim here of this project is more to show the concept and the approach in general, the idea of the approach, how that can look like when these models are fitted to tracking data, what kind of insights we can get here about the underlying tactics of the team. And this would, of course, work a bit better if we have more data from more matches. One could also compare the decoded states to other measures. So for example, to the expected goals, or the expected possession value, or to the expected threat, which we've seen in the previous talk. And what we would like to do in the future is to pool data from multiple matches, simply to have some more kind of data to maybe provide a better classification, and also to include some covariates. So for example, the score or the strength of the opponent would be very interesting here, because for the score, for example, one could then investigate how teams behave if they are leading or if they are trailing, or one could check the effect or what changes if a team is playing against a better opponent. So these are all things which could be investigated in the future when we have data from multiple matches. Okay, but that was it from my side, and I'm happy to take your questions, or if you have some questions or comments afterwards, then just drop me an email, or you can also write me on Twitter as you like. And thank you for your attention.
Great. Thanks, Marius. Great talk. We have time for a couple of questions here. So if you have them, please just post them in the question and answer. It looks like Jyrka has a question. Jyrka.
Yeah, thank you, Marius, for the talk. I have two questions, actually. The first one is that how did you consider the team in possession of the ball when determining those states? I might imagine that the tracking data might have that information available.
So for what kind of step in the analysis? So you mean how we know which team has the ball, or what do you mean?
When you're interpreting those underlying states where one team is attacking, one is defending, did you use the ball information there?
No, we we did it solely based on the EPS. So we always said, so the main interpretation for us was always, if the EPS is very large and if the EPS of the other team is fairly small, then this should be a situation where the team with a larger EPS value, where they having the ball. I mean, that's a good point. One could add like something like the distance from the ball to the ball carrying to the players to really make sure that this is really the team which is having the ball. This could also be some kind of model check afterwards, I believe, to check whether the classification via the hidden Markov model, whether this results in the same situations where if you compare it with the distance from the ball to the ball carrying player, or the closest distance from the players to the ball.
Yeah, thank you. And the second question was, I saw those convex hulls. They're sometimes a bit dependent on outliers or players who are far away from the play. If there's like a lazy striker who is lagging behind, who's just walking, they might sort of expand the area covered by the convex hull of their team. Have you considered methods for dropping out players who are clearly out of the play?
And no, we didn't do this. So what we did was that we simply only considered those observations where the ball was in play, because otherwise you always have, for example, situations where the players are celebrating after a goal or something like that. So this would also some kind of bias the analysis. So these are sorted out. But I see the point. So that of course tactics might differ if one. If the striker of one team, as you said, is not running behind with running to their own goal and help the other players with the defense, we didn't check for outliers there, but this would be worth investigating, I guess.
Yeah, because I think at least in one animation it looked like the team was pressing, but it was one of the strikers sort of hanging around by the half field line. Yeah, thank you.
We have time for one more question. Mark, you want to ask yours?
Go to Barbara. I can ask.
Okay, so there's a question in the chat about how this might be used to investigate turnovers, to see if the pressing state was related to turnovers or other game outcomes as well.
Yeah, so I think that's a good point. So we could, like, if we have these decoded states, we could have a look at these situations where one team is pressing. So we could simply investigate these time points, and then we can check what happens afterwards. So, I mean, either the team is still pressing in the next second or something else happened. And this bit relates to which team has the ball. So with information on that, this could then be easily checked whether the pressing was successful or not. Yeah.
Yeah, all your work was done sort of unsupervised to those outcomes, right? And
right.
Cool.
So I guess that there are tracking data sets available where you also have information on the ball, the team which has the ball, but for this Metrica data on GitHub, unfortunately, it's not available.
Yeah, got to match it with the event data. Cool. Mark, did you want to ask your question?
No. Why don't we stop now, since we're already a few minutes over? But I'll ask it after we stop recording.
Okay. Well, thanks everybody for joining us today for the panel on soccer tracking and Australian football tracking as well. We hope that you will join us for the rest of the talks, NESSIS. And with this, I'll pass it to Mark. Mark or Scott, do you have any announcements about the rest of the symposium?
Yeah, just to remind people, the next session is at 1 p.m. today, so it'll be 1 p.m. through 2:30. And so hopefully we'll see you all then. And I'll stop recording.